I'm Magnus Myreen. But this talk is really about Andreas's work. Andreas used to be a PhD student with me, but now he's a postdoc at Imperial. So we chose as the theme for this talk this meme, the same picture, which I try to recreate here. And instantiate to say that hardware verification and software verification are the same from sort of a sufficiently corporate look at the thing. And why might one say this? Well, because Andreas's work took what I had with many others done for software and did it in hardware. So from a corporate viewpoint, they're the same thing. So this is meant to be slightly controversial because, of course, traditionally, software verification is definitely not the same as hardware verification. But in this talk, I'll then describe how Andreas took software verification flow developed for the CakeML ecosystem and adapted that to a hardware verification flow for Verilog. And the context here is interactive theorem proving. So when I say verification, I mean proved inside an interactive theorem prover. So let's start with looking at software. The motivation for this verification flow is that we want to write our software at the source level, of course, in Rust, C, or SML, or something like that, and then reason about it at that level, of course. But then, at the same time, we want to have correctness theorems about compiler-generated machine code, the machine code that actually runs. And verified compilers in interactive theorem provers provide both of these. And then you follow a flow. You have this flow assumes you have a once verified compiler already at hand. So you develop your artifact and verification at the source level, and this difficulty level of this depends, of course, of which source language you're using, and what complexity your artifact is, and what properties you want to prove about it. So that's where you sort of pay the interactive price, and then transfer of the software source level artifact down to compiler target level. That's super easy. You just run a compiler, and similarly, it should be similarly easy to transfer the verification results down because you use the compiler correctness. And then, if we look at hardware instead of software, then we can take the same thing and just sort of replace software by hardware, and then instead of source level languages like Rust, C, or ML, we have Verilog, VHDL, or BlueSpec. And we again have a compiler that, and instead of talking about machine code, we talk about nested lists. And of course, sometimes compilers here are called synthesis tools. And with Andreas Lööv's work, we get this also in an ITP because it's with the help of his verified compiler. And the same workflow applies, and here I didn't need to edit anything. It's the same difficulty levels. It's what you do at the source level, that's where you spend all your effort, and then thanks to the verified compiler, you can just easily get the other parts too. Okay, so now let's be a little bit more specific. So I'll talk about the software verification flow, how it works in the CakeML project. So this is a quite well exercised verification flow. So for instance, we have a verified clone of the whole light theorem prover and a verified compiler for a Haskell-like language. Both of them will have PLDI talks on Monday. But let's look at the crucial parts of the CakeML ecosystem. So we have two tools, and the flow is this, that you write your source code as functions in a logic. So this is your program as a shallow embedding inside the interactive theorem prover. And then the translator produces, as a proof-producing translator, that produces a deep embedding of the same program. And then once we now have the deep embedding, we can just use the verified compiler backend, and we get verified machine code. That is, then what is verified about it? It's with this, the verification is the behavioral equivalent. So the machine code has the same behaviors as the functions in the logic at the top. So the flow is you write your CakeML program as shadow embedding, you manually prove correctness, You run the translator and compiler backend, and then for 3, it's very easy composition of 3 theorems. One for the first point of your manually proved correctness, and the second point, what is the correctness theorem of the second point? Well, it's literally a theorem that says compiler applied to this source AST produces this machine code for the software part. So you get an equality as a theorem. So you compose those 2 and then compiler correctness, and you get the third one. So, as I mentioned, Andreas Lööw has adapted this to hardware, and that has also been exercised quite well. So he verified a CPU at the sort of shallow embedded Verilog level, and then this CPU is realistic enough to host the CakeML compiler as software on top of it. Okay, so this is the mapping he then did when he took the workflow and turned it into a hardware workflow. He just took instead of the CakeML programming language, he had the Verilog hardware description language. Instead of the semantics of CakeML, he had the semantics, a new semantics of Verilog. Instead of shallowly embedded CakeML programs, he had a shallow embedding for Verilog code. Instead of machine code, he had netlists and proof-reducing translator for CakeML, he had Verilog, and so forth. And yeah, instead of the CakeML compiler, he had his own Verilog synthesis tool called Lööw. So, of course, it's not just all of this wasn't super easy. There were some differences, and I'll just go through a few of them. So he embeds Verilog modules shallowly as functional programs. These describe quite low-level things like next state functions, cycle by cycle, which is, of course, a bit different from a CakeML function because that talks about from the start of execution to the end of execution in one. And both CakeML and Verilog have impure features, which mean that they don't sort of naturally fit into the functional language of an interactive theorem prover. So CakeML, for instance, has mutable state and I/O and so forth. But Verilog has more interesting things. It has blocking and non-blocking assignments and concurrently executing processes, which require some more work. And particularly, one interesting thing that he had to tackle is how to model these in a shallow embedding, where an interactive theorem prover, everything should be purely functional, or you can use relations too, but he chose functional. So his solution was to add a top-level loop for orchestrating the parallelism, and then took care to both with syntactic conditions and also with a bit of proof to make sure that he stayed in the well-defined, well-behaved subset of Verilog. There's of this, in particular with this parallelism. More differences is that Verilog is a standard language and CakeML is an invented ML dialect, and this brought with it some complications because you have to then interface more with the reality of the standard. And Verilog, of course, is ambiguous and peculiar in some places, and one of these peculiarities is that there's so-called simulation and synthesis mismatches. So you wonder, what's this then? Well, it's the behavior of Verilog circuits differ before and after synthesis, which doesn't make any sense to me. I'm coming from the software side, but my impression is that simulation semantics is what I would consider the operational semantics, and the synthesis semantics is more of a guidelines of how you should synthesize. It's not sort of functional properties like I think of. Anyway, so this created some headache, and I think his work is mostly about the simulation semantics, but he's also interested in the synthesis semantics. And also another thing compared to software is that Verilog has X values, which means that you can signal that a compiler can fill in a value as it pleases, just to make the code generation. It has more opportunities for optimization, which I think most programming languages don't have. I still have some time. So I was have these slides about why Verilog, because I assume that question will come. Why Verilog is a reasonable question, because Verilog has its flaws or peculiarities, as I put it. And then you might also say, well, that's also a question because it seems like Verilog, once you instantiated the flow, seems like an internal intermediate step. Because you start from functions in the logic and you end up with a netlist. We could potentially just replace Verilog with something else, such as a cleaner language. So the reason we chose to stick with Verilog is that Verilog is a mainstream language, and Andreas was particularly interested in using these components separately so that he could generate Verilog from functions in the logic, even to Verilog compilers or synthesizers that aren't his own. And then he wants to stay in sync with the mainstream Verilog. And similarly, you might want to compile someone else's Verilog AST with the synthesis tool. So, as I still have a bit of time, I'm going to talk about what Andreas has been working on since. He's been working on a more detailed formalization of the Verilog standard. So Lutzig and the translator tool are based on his own formalization of the Verilog standard that he phrased so that it would fit what he tried to do. But with a more detailed semantics, he wants to be able to justify some of the simplifications he did during in the semantics he uses currently. And just to show you something of the Verilog standard, it says in some places it talks about the cycle-based semantics, and in other places it talks about an event-based semantics, and that these differ in a number of scenarios with not much more detail than that, which is not very helpful as a standard goes. So he hopes that by formalizing more of Verilog, he can find what these really mean and relate the two in some way. And since I still have a little bit of time, I'm going to talk about this. Well, formalizing Pro Standards is, of course, a messy process. It has been done for C and JavaScript and many languages. And in theory, it means you read the pros carefully and write the semantics carefully. In practice, it's an iterative process that tries to balance input you get from multiple sources and so forth. And it's important to check the quality of the results somehow. And I think in the hardware community, a traditional evaluation is to have an extensive test suite to make sure it sort of makes sense. And what Andreas is working on is maybe not alternative evaluation, but sort of another way of understanding the formal semantics is to have a visualization of the semantics. And for this, he has a new visualization tool that you can try out. And here it's a quick screenshot. So the point of this is that you write your own, you write Verilog code, and then you can interactively step through it because it's very non-deterministic. So you can pick what should happen next, and then you can explore the semantics for yourself. So this is, he claims that this is the first sort of simulation, interactive simulation tool that he knows of, at least, for Verilog, where the event queue is very clear. An event queue is really the heart of the Verilog semantics. So that's what you should be thinking about when looking at the corner cases of the Verilog semantics. So this is directly connected to his new formal semantics. And that was quite a tangent because I had a bit of time. But I just wanted to advertise that we have adapted a software verification flow to a hardware verification flow without, there were differences, but there are no showstoppers, and it worked. And then as a bonus, there's a bit about this new visualization tool. And that's all for me. And then questions after the next talk.
Yes, thanks very much. We'll have questions after the next speaker.